Hello and welcome. In this problem, carbon dioxide and hydrogen are coming and mixing in a mixing chamber. They're coming at different temperatures and producing an exit flow of a mixture. We are supposed to find the exit temperature as well as the rate of entropy generation in the systems. Well, we're going to use the IG mixture model, but there are two different ways, two different test steps to use. One is the binary mixture model, where we have IG plus IG model, for instance. The only two gases are allowed to compose the mixture, or PG plus PG model. And the second option is we can use the extended flow state for the NIG mixture. That is which allows any number of gases, which is a little more complicated but more general test step. So we'll begin by using the IG plus IG model and then reproduce the result using the NIG model. Okay, I've already logged into test. So let's go to the test calc page, flow states, and we'll launch the IG plus IG model. HTML5 version, and here we go. The two gases, as you can see in this model, binary mixture model, you select the gases first, carbon dioxide and hydrogen in this case. And it's a little bit tricky here to know which one, or if you're working with a mixture, you first enter the value of XA, the mass fraction of component A, which is carbon dioxide. So if we use that as 1, that means it's a pure carbon dioxide right now, which enters at 100 kPa and 25 degrees Celsius with a mass flow rate of 1 kg per second. So what we just evaluated is this pure carbon dioxide as determined by XA here, even though we have two components here. For the second flow, we have hydrogen. How do you select hydrogen? That's the only tricky part. If XA equals 0, that means in this mixture we have absolutely no fluid A, so the entire fluid is made of hydrogen here, which is also coming at 100 kPa, but at a temperature 100 degrees Celsius. Again with a mass flow rate of 1 kg per second. So that determines the properties of the hydrogen flow. For state 3, the exit state, we know first of all the mass flow rate is m dot 1 plus m dot 2. What about XA? Well, we know that the mass fraction of, to compose the mixture, mass fraction of CO2 must be equals the mass of CO2 that is coming, which is m dot 1, divided by m dot 1 plus m dot 2. I could just write down 0.5. We know it will be, mass fraction will be 0.5. So if we know just the mass flow rate and the mass fraction of CO2, that's not enough to find the state. We also know the temperature is constant, P3 equals P1 or P2. That's also not enough. So we use the fact that it's an adiabatic mixing. So we go to the IO panel and let's set up an equation. J at exit must be equals what? The flow energy at the exit must be the total amount of flow energy coming. J is basically enthalpy. M dot 1 times J1 plus M dot 2 times J2. This is all the energy that is coming in. That must be divided by M dot 3. Because we have already computed M dot 3, therefore we can find J at exit, which is evaluated as values. But we'll go to the state panel and we'll put the equation there. J is how much? J3 must be J at exit. So that determines the final state, the exit state. So it's, in Celsius, it is 95.7 degrees Celsius is the answer. To determine the entropy generation rate, we can figure out S dot gen must be equals what? The entropy that is going out, m dot 3 star S3 minus m dot 1 star S1 plus m dot 2 star S2. See if it makes sense. The entropy generation must be the entropy at the exit that is flowing out minus the total amount of entropy that is coming in. The difference must be the entropy that is generated. Did we do it right? No. That looks too high. Forgot to subtract. So m dot 3, the entropy going out minus what is coming in. I put a plus there. So the correct answer is reproduced. 0.7969 kilojoules per kilowatt per Kelvin. All these answers are in SI units. So this must be in kilowatt. This must be in kilowatt per Kelvin. Okay. So now let's do the same problem, but this time using the NIG model. So we'll start a new tab. So go here, thermofluids.net. Since we are logged in, we don't have to worry about logging in again. And we launch the NIG model. Note that if we use the NPG model, it's very similar. There is barely any difference except CP is assumed constant in the PG model. So you go to the HTML5 tab. The interface looks a little more complicated, but actually it's really easier, more intuitive to use. So mixture A is what? We have carbon dioxide coming in. It's not really a mixture. So it's pure carbon dioxide. We just put 1 kg. It doesn't matter, whatever unit we choose, kg, kilomole, percent. We can put anything. It's pure CO2. Mixture B is pure hydrogen. Add to the mixture, so we get pure hydrogen here. And mixture C, we have a mixture of hydrogen, which is coming at 1 kg per second, and CO2 coming at 1 kg per second. So notice that it automatically calculates the mass fraction, mole fraction, and shows it in a pie chart what is coming in. The lion's share in mole is hydrogen, obviously, because hydrogen is so light. Okay, so now that the mixture is composed, we go to the state panel, and what is coming at mixture A is which means carbon dioxide coming at 25 degrees Celsius, and mass flow rate of 1 kg per second. Notice that we don't worry about mass fraction, etc. anymore, because mixture A already means there is a pure CO2 flowing. So for state 2, we'll choose mixture B, which is hydrogen coming in, 100 kPa at 100 degrees Celsius, if you recall the problem. And it's coming at 1 kg per second. So state 2 is calculated now. And for state 3, which is mixture C, again it's 100 kPa and it's going out. We don't know the temperature, I'm sorry. And mass flow rate, of course, we know would be m dot 1 plus m dot 2. That's not enough to find the state. So we go to the IO panel and we use the same kind of equation. J exit must be equals the total energy coming in, m dot 1 star J1 plus m dot 2 star J2 divided by m dot 3. So this is exactly the same J that we found with the binary mixture model. So we can go and set up here that the exit flow energy equals J at exit. And that computes the entire state. And notice that it also calculates the partial property of hydrogen, partial property of CO2. So the NIG or the NPG model is much more versatile. And of course, you can go to the IO panel and find out the entropy generation this problem as m dot 3 times S3, the entropy that is leaving, minus entropy that entered through channel 1 minus entropy that entered through inlet 2. So, did I make a mistake? I must have. Yeah. Instead of S, I wrote J. So we go and correct S. S1 is the entropy entering, and not J, it's S2 that is entropy entering. And there still is an error. What did you make a mistake? Oh, there's a star missing here. Okay, let's see. Third time is the charm. Yes, we got the same answer that we got from the IG plus IG model. So what is the big difference here? Notice that we could use as many more mixture. Instead of just CO2 and H2 coming, we could say another gas is coming through another inlet. We can have as many inlets as you want in this problem. So that's how the NIG or NPG model generalizes the binary mixture model.